Welcome, everybody. My name is Vincent Lenar, and this is our third session in the Formal Methods February live demonstration sequence, I would say. I used to say there will be 5 demonstrations, but I'm happy to announce that there will be a sixth one in March, so somewhat breaking the nice name, but we are still happy to have another talk about consistency checking this time. As usual, I would like to introduce the Formal Methods Working Group to you and the systems modeling community very shortly. Jane, can you go to the next slide, please?
Yes.
Thanks. So we are the Formal Methods Working Group. Our mission is basically to facilitate the application of formal methods on kernel and SysML v2 models and demonstrate the power of formal methods, just to reflect on the title of today's presentation, in model-based systems engineering. We are going to do a couple of things, for example, come up with domain-specific libraries, maybe create a transformation framework to formal languages, but in general, the goal would be to cooperate on making this happen finally. If you want to join us, you can do so. You have to join the Object Management Group's SDO, Standards Development Organization, or the SMC directly. If you move to the next slide, you can see the details of how you can do this. If you are already an OMG member, joining the SMC is free, but you still have to apply through a form. You can see the link on the slide. And if you have any questions about this, you can contact me directly. You see my email address there. If you're not an OMG member, you can either become an OMG member. This is the suggested way for academic members. And for everybody else, there is a modest fee for joining the SMC only without the SDO. And with this, I would like to turn it over to Jamie. The floor is yours.
Great. Excellent. So I'm going to switch back over to here. So good morning, good afternoon, good evening, everyone. My name is Jamie Smith. I'm with a company called Imandra, and I'm joined today by Dr. John Hester. And we're going to talk about SysML v2 and how we're using Imandra to perform formal verification and other automated reasoning applications. Today, we're actually going to walk through some slides to set some things up, but then what we're going to do is go into Jupyter Notebook and show some things, proving some properties, and then John's going to take over and show some additional exciting work he's doing around automatic conversion. So with that said, SysML v2, as well as what we're doing in Imandra in the working group, are all trying to address some of these issues around model-based systems engineering. I think we'd all agree that the complexity is going up with these systems. Teams are getting larger, and communication and collaboration between these teams is getting more challenging. And requirements management in verifying the behavior of our models, as well as our compliance with the requirements, is getting increasingly challenging. Now, Imandra has applied our automated reasoning platform to these challenges in other industries. We're a company that's been around for about 10 years. We have a software as a service automated reasoning platform that uses symbolic AI and other approaches to do things like formal verification and constraint solving and symbolic reasoning. We're used a great deal in the financial sector, and then we've done several contracts with the Department of Defense. And with SysML v2 coming online, we're really excited about the formal semantics that language represents and what we'll be able to do there. And this working group is really exciting for us, and the feedback and the ideas we're getting for the community is phenomenal. So here's some of the things that we're working on and we're going to show today within the Imandra environment is taking a SysML v2 model and initially doing some model checking. So today we're actually going to show proving determinism of a state machine, but there's other things we can do as well around reachability and stability and so on. I'm going to dig into those in just a moment. We also could prove more complicated requirements and constraints. So we're actually going to do an inductive proof to prove that a particular constraint is always met by the SysML v2 model. And then in addition, we're going to talk a little bit about some of the things we can do around other forms of reasoning. We can do things where we can explore the entire SysML v2 model to learn properties of that model. We also can point our tools at a particular model and discover lemmas and things that are true about the model to give you a foundational starting point for doing formal verification, and also prove equivalence and changes of things that happen as your model evolves as you go from one version to another. The two SysML v2 models that we've been spending the most time with is an automatic emergency braking systems model and a model of a traffic light, which seems to be quite popular in SysML. The demos that we're going to show today are mostly around the traffic light, but I'm going to show some visuals of the emergency braking system model to explain some of these basic concepts to people that are maybe newer to formal verification and model checking and automated reasoning. So to dive in, we're going to explain some of the concepts of model checking using this automatic emergency braking SysML v2 model. So here's the state diagram of the model. It contains 9 states, and then there's several transitions and variables, but the heart of the model is here. When it's in operation, it's checking sensor values and then determining whether or not it should provide a warning to the driver. Forward collision warning is the FCW. If it should start applying braking automatically or apply full braking. So here, we're going to zoom in and explain some of the concepts of model checking, just looking at this part of the state diagram. So the demo we're going to show today is actually around determinism. And when we prove determinism, we're actually proving that when you're within a state, there's only one legal transition out of that state at any given time, or maybe there's no legal transition out of that state at a particular given in time. If you're ever in a situation where you have 2 legal transitions out of a state, the behavior of the system is ambiguous and can lead to a lot of bad outcomes. Other things that we can do is prove reachability. So prove that every state within your system can be reached from every other state. We can also prove that you don't have any states that represent deadlock where you get into the state and you just can't get out. And then another thing is stability. This may be okay for your system, but it's good to know if you have any states that the moment you enter, you immediately exit that state after one tick of your state machine. All right, so I'm going to hop over and demo the determinism using Imandra operating on a SysML v2 model of a traffic light. So this traffic light model has 12 states. There are 18 transitions between those states, and there are 45 attributes. Some of the attributes are Boolean values, and some of them are floating point values that have ranges from -infinity to positive infinity. As we look through and look at the determinism, we're actually going to be analyzing this entire state space of the system simultaneously to prove that there aren't any states that have more than one legal transition at a time. So now I'm going to go over to Chrome, and we should see, we saw my schedule, we don't need to see that, close that window. But what we are going to see is a Jupyter Notebook. So John, you want to nod that you can actually see a Jupyter Notebook? Okay, perfect. Okay, so this is the Jupyter Notebook of the SysML v2 model of the traffic light. And it has things in it like ports and calculations and constraints. There's also parts like the lights and the light housing. There's a controller that has a long list of attributes. There's actions, and of course, state transitions and the states themselves. When we transition through states or when we're within states, we call actions that actually change the behavior of the system. Now, we've mapped these concepts from SysML v2 into a Imandra modeling language, which is the environment that we use or language we use to perform formal methods. This is a pure instance of a language called OCaml that some of you may be familiar with, some of you may not. It's an open source language, and we have our own version of this language that we use for formal verification and other forms of model checking and automated reasoning. This particular conversion was done manually. So I went through and converted the SysML v2 model into IML. We're actually going to show you automatic conversion a little bit later in the talk. So we have the similar concepts. We have all the parts and the attributes of those parts represented as variables. We have the actions represented as functions. As we go down a little bit farther, we'll see actually our transitions between the states and an engine for actually executing the state machine. The way this engine works is it brings in two variables. One of them is external messages and stimulus from the world around the traffic light. And then the state of the traffic light itself is contained in this SA variable, which has all of the SysML v2 states and all 45 attributes of the SysML v2 model. This particular function down here executes the state machine once, and this recursive function down here can execute the state machine an indefinite number of times. All right, so with that said, I'm going to actually run this, and we've connected to a Imandra kernel, and we'll get this particular model into memory so we can start reasoning about it. So it's come back, and I'm going to run a couple more cells that actually build up a helper function that we're going to use within our verification. So this helper function is called check state transition functions. It looks at every transition between every state and makes a count of how many state transitions are legal at any given time across every SysML state and every value of every variable. And we're going to check that this particular function either returns a 0 or a 1. If it returns any other number, that's an issue. If it returns 0, it means for those particular variables, we're staying within the state and continuing to execute. If it returns a 1, it means it's time to transition to another state. If it returns 2 or more, it means it's ambiguous and we don't know which state we should transition to. So we're going to run this, and Imandra is going to use an internal function called verify to attempt to prove that this Boolean expression of either being 1 or 0 is always true for every SysML state and every attribute value. Spoiler alert, it's going to come back false. So it comes back is refuted, but when we have a refuted verify function in Imandra, we provide a counterexample. And what we see here is we have a problem with the read on state. And then here are values for all 45 other variables that led to this ambiguous state transition. As we dig in and look at it, what we learn is in the read on state, we either go to traffic flow, which goes back to change operations or manage errors, or we turn the green light on. What we learn is that we are not explicitly checking that there's no error in the system before we move from red light on to green light on, which could be a huge safety concern. We would hate to turn the light from red to green if we're in some kind of error state. So if we go through and make the correction and reload the helper function, we can run the verify again, and Imandra comes back as proved. So now we've cleared up the lack of determinism, and we have proved that the state machine is deterministic, meaning that there's either 0 or 1 legal transition at any given time. Imandra provides details around the proof that you can put through, that you can put through an external proof checker if needed. And there's that. So as you go down and look at the SysML v2 transition functions, here's the transition functions before we made the change, and down here is the transition functions after. We just added this term to our Boolean expression, and now everything is working correctly. Now, it's pretty easy to leave one of those Boolean expressions or terms out of your expression, so it's nice to have these type of checkers in place to find issues with our code. So with that said, one thing I want to encourage is please put questions in the chat, and we're going to go through those questions at the end. And And again, we'll be around for 20 minutes or more to continue the discussion and answer those questions. Okay, I'm going to go back over to the slides. And now we're going to do something more sophisticated, where we're going to prove that a constraint is always met within this traffic light SysML v2 diagram. The constraint was actually written in SysML v2. For those of you that aren't as familiar with the textual notation for SysML v2, we have up here a constraint definition of power, where we sum up a collection of powers and compare them to a limit. This is an assert of that constraint, where we explicitly declare the parts that are going to participate in this power usage constraint, and then a limit of 19 watts. Now, we can't just sum up the power of all these parts, assuming they're on, because if we did that, we would end up with a power usage of 43 watts. So when we prove that the power never exceeds 19 watts, we're proving a lot of behavioral properties of the system as well. We're proving that no two lights are on at the same time, or a light in the radio is not transmitting at the same time, and so on. All right. So I'm going to go back over, or actually, excuse me, I'm going to advance here and explain the process of doing the inductive proof. It's a 5-step process. The first step is we define the attributes of what we call a good state. And I'm going to show you an example of good states for this traffic light, and then we'll go through the other 4 steps of the inductive proof. So again, there's a reason those are muted out at this time. So we define the good states by specifying 7 of the 45 attributes across all of the SysML v2 states. We specify things like the power is on. Okay, that's a good thing. But we also specify that when the controller thinks the red light is on, the red light is actually on when we're in the red light, a red on state. Or when we're in the yellow blinking state, the controller thinks the yellow light is blinking and the yellow light is actually blinking. So here is a complete collection of our good states. And we will use that to first prove that when you start in one of these good states, after a single execution of the state machine, you remain in a good state. Then we will use that to prove that once you start in a good state, no matter how long the state machine runs, you'll remain in a good state. Then we need to start from somewhere. So we'll have an initial state, which in this case will be going from power off to power on. We'll prove that that is one of these good states. Then we prove that every good state is less than 19 watts. And then we bring it all together to do an inductive proof to prove that if we start from power off, go to power on, the system never exceeds 19 watts, no matter how long it runs, because it's always in one of these good states. Okay, take a breath. I'm going to now go back to the Jupyter Notebook, and we're actually going to see this happen. Okay. All right, so now we're back in the Jupyter Notebook. So here is the representation of the good states. You can see these are the SysML state in the 7 attributes that we constrain. And this is a Boolean expression that really returns a true if you're in the good state and a false if you're in any other system state. So we'll run this to declare our good states. Now we're going to do 2 proofs. The first proof proves that if you're in a good state, using that function we just declared up above, and we run the state machine once, you remain in a good state. Then we're going to use this lemma here to prove that if we start in a good state, we can run the state machine an unlimited amount of times and we'll remain in a good state. So we're going to run it, and I want you to make note of how quickly it executes. Comes back pretty quick. We've proved that for one iteration of the state machine, if we start in a good state, we'll remain in a good state. And then we also proved that if we start in a good state and run it indefinitely, we'll remain in a good state. Now we're going to set that initial state where we're going to start in the off state. And in this initial values for this attributes, the power is on. So we're going to prove that that is one of our good states. And then we're going to use that initial state combined with the two lemmas above to prove that if we start in that initial state, we remain in a good state no matter how long we run. This also comes back as proved and proved. Now we're going to bring it all together. We're going to bring in the concept of power. So we're going to prove that every good state uses less than 19 watts. And then we're going to do an inductive proof where we prove that if we start in that initial off state, we run the state machine for an indefinite amount of time, we're always in that. We're always under 19 watts. So we run that, then we come back, proved and proved. Now, before I hand things over to John, what I'd like to do is show some of the things we can do around system exploration. So down here, we have a diagram as a result of running a function that we call modular decomposition and show region decomposition. This is a representation of the SysML v2 model of every invariant state of the system. Before I ran the modular decomp, I actually constrained the system a little bit. I said, only show me states where the clock is running and the power is on. If you don't set those constraints, you get a lot of duplicate states that look very similar. But I can come in and I can click on this particular region decomp and go in a little bit deeper and see that, yeah, here are all the states in my system where the clock is running, the power is on, and we're in an operational state. If I go and look at these collection of states out here, this is when our system is in an error state. So we could explore those if we like. And we can just continue to dig down and see different regions where we have different constraints. If we get all the way to the bottom, we'll do that over here. If we get all the way to the bottom, like here, we have a series of constraints that lead to an invariant result. So as long as these constraints are true, this is always the result that you're going to get. So this collection of states is an infinite state space, but we're able to break it down into 174 discrete states, some of which have an infinite range on some of their values. Now we could do this type of exploration, but we can also point our tools at a model and learn properties about that system. And we'd love to talk more about that, but we're not going to get into that today in detail. So with that, please type any questions you have in the chat. I'm going to turn things over to John and let him talk about some of the things we're doing around automatic conversion and integrating with generative AI and LLMs.
Sure. Hello, everyone. My name is John Hester. I'm going to be talking a little bit about our transpiler that we've been building to automatically convert SysML v2 models into this Imandra modeling language that Jamie was showing you some of before in the Jupyter Notebook. The idea is that with this automatic transpilation into IML or Imandra modeling language, it would allow people that are working on models to benefit from some of the powerful features of Imandra and formal methods tools in general without having to become domain experts themselves. So ideally what we'd like to be building towards is not only just converting the actual elements of the model, but looking at things like verification goals and automatically generating verification goals for you based on your SysML v2 constraints, requirements, verification cases, this kind of thing. So this way you can use our tools with not having to become an expert in it. So we are able to do model checking and complex formal verification of requirements, proofs. These are all things that Jamie was showing you just a moment ago. And one of the other things that we'd like to provide is a large language model chatbot that is able to allow users that aren't necessarily domain experts even in systems modeling to be able to ask questions about a SysML v2 model, and at the same time have a guarantee that the responses that they're going to get back are going to be hallucination free. So I'll talk a little bit about how we're going to do that at the end as well once I'm done giving a short demo about the transpiler. Could we get the next slide? Great. So here we have three little boxes. What's being shown here on the left is some SysML v2 source. This is just from a simple model that we've been working on while we've been building out the transpiler. We have a part usage for something of type stool, and we have several subparts that make sense for a stool. We've got a seat, which has mounting holes. We have legs and the leg mounts. So the first process that goes through in our transpiler is we need to get the JSON representation of our SysML v2 model. So for now, the way this is working is we are programmatically generating and executing a Jupyter notebook in order to publish this SysML v2 to an instance of the SysML v2 API server. So once we've submitted this to the server, we're able to get the JSON representation in the middle back out from it. And then the Imandra SysML transpiler, it operates on this JSON representation, and you get the Imandra modeling language file back out. So this truly is a end-to-end from a .sysml file to a .iml file. And as we continue to work on this, we're going to support even more fragments of the SysML v2 language and architecture. All right, so I think that we're ready to begin the video. So I have two short videos that we'll walk through, and we're just going to show this transpiler in action. So whenever you're ready to start the video, Jamie, on the left, we have the SysML v2 model. And on the right, we have a corresponding JSON representation of this SysML v2 model that we've requested back from the API. And in this SysML v2 model, we have a part definition for the vending machine controller, a default controller with just power on and abort false. And then our state machine definition, we have several states: idle, accepting coins, select product, etc. We have an input controller, and then we have the transitions between these states. And as you can see, this is all represented on the right. So we'll just quickly run the transpiler in the right window. It comes back quickly, and you can see that it says we've created an output file in out/generated.iml. So this is the resulting file that we'll pull up now. And as you can see, we have a file here of Imandra modeling language that has been automatically generated by our tool. And of course, right now we're only working with a fragment of SysML v2, but we intend to support as much of the language as possible. So we have all of the states that were present in our model. We have transition functions. These correspond with the individual transitions that are declared. So you can see we've got abort to return coins, etc. We have representations of these guards that prevented certain transitions or allowed certain transitions to happen. We have these meta functions that capture situations where there are multiple transitions that we could do from a given state. And finally, here at the bottom, we have a code-generated general transition function that captures the idea of a single step of your state machine, and also a code-generated multi-transition function where you can do multiple steps of your state machine at once. So already this transpiler is in a state where, it's developed enough where if you're wanting to verify things about state machines, it's pretty usable right now, where you can generate IML, and then if you are interested in playing with IML, you can do real proofs about your SysML v2 state machines. All right, so this was generating the IML, and so now let's load it up in Imandra. So could we go to video 2? So rather than using the Jupyter notebook interface that Jamie was showing earlier, I'm going to be showing the use of our command line interface here. So the first thing we're going to be doing is loading this model up in Imandra, which is what we just did there. So now we're going to open some of the modules that correspond to the package and part definitions or state machines. So we're doing that right now. And then we're going to try to do some basic proofs about our simple vending machine state machine model. So what I'm writing right now is a verify goal where we'd like to prove that if we do a step of our state machine, then we end up in a different state. So this is very similar to what Jamie was showing earlier. And we get back a counterexample saying that, all right, well, if we are originally in the idle state, the power is false and abort is false, then we actually remain in the idle state here. So if we decide that this is intended behavior, we can change our verification goal to be more close to what we intend. And let's say that we want to use our default controller where the power was true. And so this default controller was a part usage that was defined in our SysML v2 source file. So our verification goal succeeds. And so now we're going to use a different Imandra syntax using this theorem notation. And so we want to prove that we're always going to dispense a product after selecting a product for an arbitrary state machine X and arbitrary controller. And we're going to make this theorem as an implication where we'll say that we're wanting the power of the controller to be true and the abort to be false and X to be in the select product state. And we're writing now that this implies that our transition function will result in the dispense state. So we run this, and fantastic, we come back with a theorem proof. So this is very exciting. This is essentially proving using a full first order theorem prover properties and facts about SysML v2 state machine models. All right, so I think that we're finished with the video demos here. Jamie, do you want to go back to the slides? Thank you. So briefly, I'd like to talk about our integration with large language models. This is something that we're already doing with some of our financial clients. So this is something that we'd like to bring to the system modeling space. So we're going to connect natural language interfaces to SysML v2 models and allow various stakeholders, anyone that's interested, to understand the design, ask questions, and perform critical tasks without having to ask questions about models without having to necessarily approach someone and ask them a question while they're working on it. So one of the major advantages of this is that we're going to be able to provide responses back from this large language model query interface that are going to be hallucination free. This means that it's not going to be making up information about your SysML v2 model. The way this works is that the large language model is actually used to convert your natural language question to the large language model into a number of predefined queries that the large language model is allowed to run. So this means that whatever information you get back from your large language model interface, the answer is going to be something that is actually true and is correct information about your model. So this avoids a whole lot of concerns about integration of large language models in design spaces, the concern that it gives you bad information back. So we can avoid that whole issue. All right, wonderful. I think that I'm through here, Jamie. Would you like to wrap things up?
Yeah, I'll say just a few closing comments, and then we'll open things up for questions, and I'll look at the chat. So again, just what we're trying to do is we're trying to integrate our model checking and model verification as seamlessly as possible with current model-based systems engineering tools and workflows. We want to integrate natural language to increase productivity of systems engineers, as well as allow other stakeholders to participate in the process. Because one piece of feedback we hear is there's people who know SysML, there's people who do not, and that creates a divide within organizations or larger communities. We also are working towards tooling and ideas to automatically build out verification goals like the inductive proof we did around. helping people define their good states and iterate on those types of proofs. And then finally, we're going to leverage the API. John's already doing that, and he's had a lot of success. So we can work with models that are being worked on in one tool from a particular vendor, or models worked on another tool from another vendor, and bring those things together and get the same results. We're going to take some questions now, and I'm actually going to stop sharing. If you want to have additional conversation after our time today, my email is there at jamie@imandra.ai, and John's is john@imandra.ai, and John has an H in it. So it's pretty easy to remember, and you can, that's right, John? Email? Yeah, okay, perfect. Okay, so now what I'm going to do is I'm going to stop sharing, and I'm going to now bring over my window and start looking at the chat and see if there's any QA or chat. So I clicked on the QA, here's the chat. Okay, we'll go up to the top. Can you see these two, John? Okay, do you want to take this one? Because I think this is directly a transpiler question.
Sure. So at the in the chat, I see. Thank you for this presentation. I want to ask two questions. First, what translation language have you used to automatically generate the result to apply the formal verification on it? So we have written the transpiler in OCaml. So in OCaml, we are parsing the JSON representation of the SysML v2, and then doing all of the translation to OCaml. IML really is the pure fragment of OCaml. And so we are generating OCaml from an OCaml program. And the second question here is, do you apply formal verification on the translation itself or not? At the moment, we are not applying any formal verification to the transpilation, but that's something that we could definitely look at in the future.
Hey, John, could you speak to some of the automatic things we get when we convert from SysML into IML? Or automatically checking things like termination and those types of things?
Right. So whenever you've written a function in IML or a function that was originally written in SysML and transpiled to IML, one of the benefits of even loading this into Imandra in the first place is you're already getting a formal property about your model just because of the fact that it's been loaded. Whenever it's successfully loaded, this means that we know that these functions are going to terminate. So you're not going to get caught in a infinite loop. So okay, so the next question here, can we check to what query the LLM transformed our question to in order to ensure that it's working correctly? Absolutely. We can echo the queries back as well.
Yeah, and we actually maintain a full audit trail. So we see the query, we see how the query was converted into the semantics that we use to reason about the query. We show the result that Imandra generated based on that query, and then we show the result that the LLM actually represented to the user. So we can maintain that complete audit trail. And because Imandra is doing all the reasoning and we've constrained the types of legal queries, if someone asks an outrageous question like who won Best Actor in the 2020 Academy Awards, we would just send a message back that that's not a valid query. Or even if it's a little less, extreme as that, let's say somebody says, can you tell me the power consumption for the housing of the traffic light? An LLM might give you an answer, 2.2 watts, but we would say, there is no power usage attribute for the traffic light. So we would actually give you a result that's maybe not what you expected, but is correct. I hope that answered the question. And that looks like it's from Sandor. And the first question came from Racine, I believe.
Yes.
Thank you guys for the question. Now we have another one here. Go ahead, John.
From Benedict, what language elements do you support in state machines? So right now, we only are able to support a fragment of the SysML v2 language in general. This is also true for the state machines. This is a daily work in progress as we are adding support for more and more elements of the language. The entry, exit, and do behaviors, one of the very first things that we're going to be working on is supporting the do actions. So say, for instance, if you are wanting to assign some variable to something in SysML v2 inside of a do action, then that's one of the things that we're working on. So I don't have a list of the exact supported elements yet, but for now, the plan is as much as possible, and we're continuing to build it out.
Sounds great. And one thing is, in that traffic light example, which I'm happy to share with anyone, and there's a few articles, we do go through and we did a manual conversion of entry, exit, and do. And we're members of this working group, and we're excited to be here. We're also are participating in the executions working group. So as a particular behavior or execution model is refined for those types of actions, we're going to continue to evolve and update our transpiler and the behavior in Imandra IML to make sure it's consistent with the findings of the execution working group. But thank you for that question. That's a great one. And personally, I had a lot of confusion around the do action as I read through the PDF documentation as I was trying to do my translation. So I think there's some uncertainty there on exactly how those things need to operate still. I'm looking forward to nailing that down with the team. Okay, next one. Yeah, so the question is for the manual I'll talk about the manual side, and then Johnny, you can echo on. So started with parts and ports and connections, right? That's where I started because that's kind of the structural parts of SysML. It's like the foundational pieces. So that's where things started. But then, of course, formal verification and model checking is more powerful when we start to get into behavioral systems. So we have looked at state machines and the actions associated with state machines and their transitions. There's other forms of behavior that we have not done much work with, but we plan to. Hopefully that answered your question. Do you want to add anything, John? Okay, perfect. Okay. At this point in development, how much do I need to understand OCaml to leverage Imandra prover technology or tooling, or can I use the chatbot? Okay, so I'll say a couple words, John, and then you can say a couple words. So, our goal is to this year or into very early next year to have integration through the API with most, if not all, of the tool vendors who have public releases of SysML v2 and be able to do model checking and some of the proof technology automatically. Now, there's things that you could learn about OCaml and using like the terminal interface that John was showing that it's about as difficult. So I was new to OCaml within the last year or so. It's about as difficult as learning, another programming language. So it's not overwhelmingly challenging. And if you use examples, you can build things out on your own. Now, we are targeting to have our first large language model demo applied to SysML v2 sometime within the next quarter. We may have it a little bit sooner, may happen a little bit later. We're showing we're showing large language models and chatbot interfaces to other things already, and we're actually releasing and deploying those. But we're getting a little bit of a sneak peek here today. But one of the first things we want to do with that chat interface is to allow people to synthesize constraints and requirements, and then have us automatically attempt to prove them. So that's a starting point. And if people on this call have other ideas, like, man, if I had a natural language interface where I could ask this question or synthesize this SysML, we would love to hear from you, because we're newer members to this community. And so there may be pain points that we don't know about. And we'd love to learn from the experts here on those pain points. Okay, anything to add, John?
So as far as using the chatbot exclusively, one thing that we'd like to be able to do as far as using formal methods for SysML v2 models is to allow the user to say something along the lines of create a verification goal saying that my power usage is always going to be less than 19 watts, that kind of thing.
Right. That's right.
So at this point in the development, I would say that if you want to actually be doing the proofs yourself, you would need to have some knowledge of OCaml, and using the chatbot exclusively would not be enough, but we're building this out.
That's right. That's right. Thank you, John, for that clarification. For this, do we need any other tools, or Imandra is enough? Is there any system need configuration required? Do you want to take that one, John?
Yeah, sure. So I'll really briefly say that there would be 3 components that you would need to essentially run the stuff that we've shown today. Well, maybe 4. To be able to do everything that we were showing today, first of all, you would need to have the Jupyter kernel for SysML v2 set up. You would need to have the Imandra kernel for Jupyter set up. You would need to have the API running locally, the SysML v2 API running locally, that is, and then also a running version of Imandra. So that could either be running through our cloud interface. We have a playground where you can, even without installing anything, you can copy and paste IML into it and be able to run proofs. As far as system need configuration, I would say that it's pretty straightforward. I don't think that there's any complicated configuration that's necessary, other than one tricky point is that within there's a JSON file somewhere in the API directory where you'll need to tell your Jupyter Notebook whenever it's publishing your model to actually use the locally running API rather than the one that's hosted on the InterCAX, if I remember correctly.
Thank you, John. So Barry's got a question here. Do you want to take this one, John, as well?
Yeah, so how do we know the transformation from the SysML v2 to the target language is isomorphic? This is something that is on the top of our list of concerns and something that we're taking very seriously. Of course, we need to have this transformation be kind of isomorphic or semantically equivalent to the source SysML v2 model. So at the moment, we're reading the spec very closely and participating in various working groups to make sure that we're staying on target with the semantics of this.
Excellent. And then I'll take Sandy's question. Thanks for attending, Sandy. So how will this scale to large models? So, we're going to need to work and build out tooling and techniques to allow the performance to scale as the model scale. And I think it's a very attainable goal. There's different things that we have done where we have done formal verification on extremely large models that are not SysML v2. One example is a public exchange for a stock exchange, or a private exchange for a stock exchange. Having a model of that and being able to formally verify properties is something that complex. The example we talk about most is with Goldman Sachs. They're one of our customers, and they have an exchange they use to transact with other banks and public exchanges. And we formally verify that exchange through a long list of verification goals and properties. And we've also done work around very large public exchanges as well. So those are examples of incredibly large models, incredibly complex models where we're achieving the goals. But I think that this is going to be a bit of iteration and a little bit of invention that's going to be happening. But I believe very strongly that formal methods applied to SysML v2 has the potential to become a ubiquitous tool that is used on simple models and extremely complex models. But it's going to be a journey. It's going to be a journey to get there. John, do you have a comment on that one?
Yeah, not directly to the scaling, but as far as the isomorphic transformation to IML, I would say that another benefit of our approach of running this IML would be that if as execution and simulation tools for SysML v2 continue to proliferate and evolve, you can of course co-simulate with other tools, and if there's a discrepancy between what results you're getting back from us and the simulation from another tool, we would be very, very curious about that, of course. And that would be a good way of shaking out discrepancies.
Yeah, awesome, John. Thanks. Okay, ask about audit trail for the system. So do you want to speak to plans for a form of audit trail within the transpiler and our proofs, John?
Yeah, so I'm not exactly certain what is meant by audit trail. The idea there is that we're trying to stick as close as possible to the formal semantics of the SysML v2 language, and so we can track what element is transformed into what. We can also be able to show step by step how this transformation is happening.
Okay, excellent. So Barry asked, what plans do you have to see how these approaches scale? Yeah, so it's kind of related to Sandy's question. So we're going to be wanting to focus on the most common challenges first and making sure that we're able to perform the formal methods and verification on those challenges as models scale. One thing we're going to need is models. So here's the plans. One is Sandy's starter model, the flashlight, for anybody who was at the Nkosi event. He talked about that. We want to do formal methods on that starter model. Then there's the CubeSat. So we want to, when that gets converted to V2, and we believe that there's community members at Nkosi that are going to convert the standard OMG model for CubeSat from V1 to V2, we'll start doing formal methods on those types of models. But the easiest way to build out techniques and tooling to scale is to get bigger models and solve real problems that the model-based systems engineering want to solve. So our plan is to react and adapt to the community and the types of models we get our hands on. Excellent, thank you. Oh, I have two other questions. Okay, but we got. How much more do we have here? Do we have? Okay, I'm going to stay on.
More questions, and then there's also questions that are in the Q&A tab that we should address also.
Oh, I see. Should we? Why don't we hop over to there? Oh my goodness.
Well,
okay. What?
Very quickly, Rasim asked, I have two other questions. Does your work support functional and non-functional properties of system modeling? I'm assuming that you mean functional in the sense of pure versus impure. And the idea is that we are going to, and currently are supporting some non-functional properties. So there are definitely methods that we can use to take an occurrence of something impure or non-functional that occurs in a SysML v2 model and transform it into something that is pure that we can represent in our fragment of camel that we're using. So yes, we intend to support both. Why didn't you try to use a standardized transformation language like QBT, which is standardized from OMG? This is something that we can definitely explore, but at the moment we have no plans to use that, but we can definitely look into it. Thank you for the suggestion.
All right, I'm moving over to the Q&A section because people have been very patient. Oh, there's only a couple in here. Okay, so thank you for the presentation. I want to ask two questions. Oh, we got that one already, I think. So what language do you use to translate? Okay. Yeah, we got that one already. That showed up in the Q&A. How do we know that the transformation system OV2 represents the target language as isomorphic? We got that one as well. So now we're going to go back over to the chat. All right, so if I go back up to where we were, okay. So Antone or Antony has a question. We are also working to connect formal models with large language models. Model to Beck. I'm reading it. Okay, I think this is a good one to take offline. So this area around different approaches for integrating with LLMs, unless John, you want to hit this one, I think it'd be great to have a conversation offline on this if you want to shoot us an email or reach out.
Absolutely, I think that this the approach of looking directly at the model with the LLM is a little bit different than, if I'm understanding correctly, is a little bit different than the approach that we're taking. Our approach is to allow the LLM to interact directly with an intermediate representation that we hold in the transpiler. So I think this is a slightly different approach, but as Jamie said, we are, of course, absolutely excited to talk about it.
And we got a little education from Conrad. He dropped information on the do function, so we can review that. Oh, I gotta log in. I'm not gonna do that right now, but thank you, Conrad, for sending that over. Provide modeling guidelines for typical modeling practitioners. Yeah, go ahead, Conrad.
Well, that tiny URL I added is open, to non-OMG members.
Got it. Typical modeling practitioners to include in the model that facilitates the reasoning with the Imandra.
Yeah, so to that question, I'd like to say that it is possible that there are going to be some features whenever we release our 1.0 of the transpiler that are going to be still unimplemented. I think that in that situation, what we would definitely do is publish a, just as you say, modeling guidelines or a style guide indicating what fragments of the SysML v2 language are supported. So this way, it's clear what works and what doesn't.
Yeah. Awesome. And there's when Vince sends out the information of this recording, what have you, I'll send out a message to everyone who I have access to their email with some links to some articles that may be helpful to look at. And then also we'll keep people posted through the community of our release cadence. If people want to play with our formal methods tools, you can go to imandra.ai right now and go to our docs section and start playing, not specifically with SysML v2, but start understanding how our formal methods tools work. We start with sort of a hello world example, it's intro to Imandra, and then we get into more complicated concepts. So I think we're right at time. So I'll hand it back over to the host with the most, Vince, and let him say a few closing words.
Thanks. I just wanted to remind everybody that I have also posted the link to all the materials in the chat. So Jamie, you can also put your anything to read or a demo or model files, anything in those folders, and then everybody can access it who joined one of these meetings ever. And if you want to follow what Imandra and others do from up close, again, feel free to join the SMC and come to the Formal Methods Working Group, because we will continue meeting even after this series of demonstrations. And most of these questions are actually open and will be interesting to discuss. So thank you for joining. There was actually one more question in the chat. If you want to answer that, I think we still have time for that.
Is it the one from Andreas here?
Yes.
How easy it is to currently express properties of interest using Imandra's framework. Properties, is it? I'm not sure I completely understand the question. John, do you have your arms around that one?
Yeah, so the expressing properties of interest in Imandra's framework, it's a programming language just as any other. And once you have this representation in the IML, the result of the transpiling or a manual conversion, it's simply a matter of looking at the relevant types and addressing the properties of interest. Sometimes it can be a touch tricky to express certain things, but the reality is that the first order theorem prover that underlies Imandra is a Boyer-Moore style prover. We also use a SMT solver called Z3. So as long as you're able to express your property, which I've not ever encountered a situation where I wasn't able to express it, hopefully we'll be able to prove it. One of the difficulties of writing a proof is that we have as much automation as we can possibly get, but there are sometimes situations where in order to prove your property of interest, you may need to add some lemmas. And as we continue the development of this, one of the things that we mentioned in the presentation is the automatic discovery of properties. So you could interpret this from a mathematical sense as automatically providing you with lemmas as well. Our end goal is to minimize the amount of mathematical know-how that's necessary for a user to provide sturdy proofs about the behavior of your system.
Awesome. Thank you, John. And back to Sandy's question earlier about large models, I think one technique we'll be using is trying to carve out regions of the model to prove properties about the model, and then bring those together to prove a more global property. And those are the types of techniques and approaches that are going to require a bit of tooling and a bit of technology and a bit of invention. But I think it's very attainable.
And also, is the formal specification based on existing SysML v2 directives? So partially, yes. You can, of course, once you have generated some IML, you could write your own formal theorems or verification goals. But we'd like a way to, and we've already done some of this for constraints in particular, automatically converting a requirement constraint or verification case in the SysML v2 language to a theorem that's automatically proved in Imandra.
Yeah. Very good. So
think
thank you guys so much. What's that?
I think there might have been one in the Q&A that we missed here.
Oh, let's go back. Let's look.
From
Is it
from
the 8th? I think it's from the 8th.
Oh, okay, yeah, right. That's okay. So that's from maybe last.
Yeah, last week.
Okay.
And
Yes, you're right.
Yeah.
All right. So thank you very much for the nice presentation. I'm looking forward to seeing what you just mentioned. I think the verification case stuff will be really interesting. We are also following that path. And also thank you for a very nice discussion to everybody who attended and asked questions. See you next week and have a nice day.
Thank you very much.
Bye, everyone. Bye. Thank you.